Okay, perfect. The topic of today's lecture is empirical risk minimization and the statistical learning framework. And first, I will briefly remind you of the key definitions we need from the previous lecture. We consider a data set of inputs labeled as X and their corresponding outputs or labels represented by Y. In supervised learning, our primary goal is to learn a function that can effectively map these inputs to the correct labels. And the data consists of samples, which we represent as X, and each sample is described by multiple features, and we refer to them as X1, X2, all the way through Xn. And the labels denoted by Y are the correct outputs for each of our samples. And each label is paired with an input, and our goal is to correctly predict these labels. And the model we develop aims to learn a function that maps each input in X to an output of Y. And this function is parameterized, meaning it has adjustable settings, which we refine during training to improve its accuracy. And yeah, these elements form the basis of our understanding of supervised learning. Now let's delve into the concept of risk in machine learning and why do we study risk? Risk analysis helps us understand how well or sometimes how poorly a model performs when making predictions. It allows us to evaluate the effectiveness of the model and determine areas for improvement. Key consideration are important when assessing risk. For example, the magnitude of risk, along with the choice of a suitable loss function, directly impacts the model's performance. And depending on the nature of the task, we can select different loss functions that measure how well the model's predicted values align with the true values. This is essential for providing a comprehensive assessment of the model's quality. And essence of model training can be summarized as a process of minimizing a risk. And training involves adjusting the parameters of our model to minimize the discrepancies between predicted outcomes and the actual labels. In other words, it's all about reducing error and improving accuracy. In our previous discussions, we touched on the idea of loss function, but we didn't formally introduce them. And now we define a loss function as a mapping that takes both the predicted value and the true label and returns a real number that represent the penalty or loss. These functions measures how far off our predictions are from the actual target values. And here you can see some key points to consider. The loss function quantifies the discrepancy between the predicted and true values. It's important in determining how well our model performs and guide us during the training process to minimize this loss. And there are different types of loss function depending on the problem at hand. For example, for classification problems, we use loss functions such as 0, 1 or cross entropy, while for regression problems, we often use mean square error. And finally, notation and perspectives regarding loss function can vary across disciplines. It's important to be mindful of these variations when interpreting definitions. They can affect how we understand and implement loss in a particular model. Let's now explore some common example of loss function that are frequently used in machine learning. We start with classification loss functions, which are particularly important when dealing with classification problems. And the first one, cross-entropy loss. This function measures the difference between the true label and the predicted probability. Specifically, if we have a true label and a predicted probability, the loss is calculated as negative y times the logarithm of p. This effectively penalizes incorrect predictions, pushing the model to provide probabilities that closely match the true labels. And the second example is hinge loss, commonly used for training support vector machines. And the hinge loss is designed for binary classification problems where the labels are either negative or one or positive one. And the loss function is defined as a maximum between 0 and 1, meaning the product of the true label and the predictions. Essentially, this loss encourages the merging between the correct classification and any possible misclassification, which is important for ensuring robustness in SVMs. Now let's move on to the regression loss function, which are commonly used when our task is to predict continuous values. And first, mean squared error. This is one of the most popular loss function for regression task. It measures the average squared difference between the predicted value and the actual value. And by squaring the difference, larger errors are penalized more, which means the model is heavily influenced to reduce significant deviation. And this makes MSE particularly effective for capturing and reducing large errors. And the second one is mean absolute error. And unlike MSE, the mean absolute error calculates the average of the absolute differences between the predicted and true values. This loss function treats all errors equally without squaring them and making it less sensitive to outliers compared to MSE. And mean absolute error is useful when you want a more balanced view of the errors across all predictions without a disproportionality emphasizing large one. And before introducing the next loss function, let me show you an interesting type of regression. Quantile regression is an extension of linear regression. And instead of estimating the conditional mean of the response variable y given predictors x, quantile regression estimates conditional quantiles. And this allows us to understand how the predictors affect different parts of the distribution of y, such as the median or other percentiles. For example, if you're predicting house prices, quantile regression can show how the 10th percentile low prices house or the 9th percentile high price house changes with factors like, for example, location or size. And traditional linear regression focuses on the mean, represented as expected value y of x. And quantile regression generalizes this by providing insights into the full distribution of y. Okay, and the objective of quantile regression is to minimize the sum of special loss function called the pinball loss function, and the optimization problem we can define as beta tau equals the argument of beta that minimizes the sum of rho tau of the residuals, where the residuals are y sub I minus the predicted value, which is x sub I transpose time beta summed over all I from 1 to n, where beta tau is the vector of coefficients for the chosen quantile tau. Yi is the observed value of the response variable for the ith data point. Xi transpose beta is the predicted value based on the model for the ith data point. And rho tau of U is a pinball loss function which depends on the quantile tau. No, and again, the pinball loss function rho penalizes residuals U. The difference between observed and predicted values differently depending on the sign. And in general, quantile regression is particularly useful in fields where understanding variability is important. For example, in economics, analyzing income distributions, and in medicine, studying treatment effects across different patient group, for example. And beyond the standard loss functions, we have discussed there are situations that call for custom loss functions tailored to specific needs or constraints in problem. One example of such a custom function is quantile loss, which is used in quantile regression. And the goal here is to estimate a particular quantile of the target distribution. For instance, if you are interested in predicting the median of the 9th percentile of the target value, quantile loss is the appropriate choice. The function itself works as follows. It assigns a different weight depending on whether the true value is above or below the predicted value. And it parameterized by a variable called tau, which determines which quantile you want to estimate. When tau is equal to 0.5, we are predicting the median. And if tau is 0.9, the function targets the 9th percentile. And quantile loss is especially useful in case where you want to make predictions that are not simply averages, but instead capture the distributional properties of the target variable, like estimating how the target behaves at different percentiles. And this makes it an invaluable tool for analyzing risks or dealing with the skew distributions. Continue with the idea of custom loss functions. Another approach is custom loss for rare event detection. And in general, detecting rare events is often challenging because these events occur infrequently and standard loss functions may not assign enough importance to such occurrences. And to address this, we can design a weighted loss function. In this custom function, we use a parameter called alpha to control the weight assigned to the rare events. When the true label is 1, indicating the presence of a rare event, the loss is multiplied by alpha, which lies between 0 and 1. And for a true label of 0, indicating a more common event, the weight is 1 minus alpha. This ensures that rare events are given a higher emphasis during training, which is important, of course, for improving model performance in imbalanced data sets. And by using this weighted approach, we are able to ensure that the model doesn't overlook rare but important event, and leading to better detection of anomalies or critical cases. And again, this is particularly useful in fields like, for example, fraud detection or healthcare, where correctly identify rare events is critical. Now let's explore the concept of expected risk. This is fundamental in evaluating a model's ability to generalize. And expected risk, sometimes called the generalization performance or test error, is defined as the expected value of the loss function between the true output and the model's predicted output. And essentially, it provides a measure of how well our function performs over the entire input space, taking into account the underlying distribution of the data. Formally, given a function that maps input data to labels, a loss function, and the probability distribution over the input-output pairs, the expected risk of the prediction function can be expressed as the expected value of the loss or as an integral over the product space of inputs and outputs. And the integral quantifies the average performance of the model across all possible data points. I should say expected risk is particularly important because it accounts for the distribution of the input-output pairs. In other words, it helps us understand not just how well our model fits the training data, but also how it's expected to perform on unseen data. By minimizing expected risk, we aim to build models that generalize well beyond the training set. As we discussed on our previous lecture, let's recall the concept of empirical risk, also known as training error. Moving from a theoretical understanding to a more practical approach, empirical risk provides us with a tangible way to evaluate model performance by averaging the loss over the training data. And empirical risk serves as an estimate of the expected risk when we don't have access to the true data distribution. And by calculating the average loss across the training samples, empirical risk helps in evaluating and optimizing our models. So given a function that maps input data to labels along with loss function and a set of training data points, empirical risk is calculated at the average of the loss over all training examples. And the purpose of minimizing empirical risk is to ensure that our model performs well on the examples it has seen during training, guiding the optimization process. However, important to remember that empirical risk alone is not always a perfect indicator of generalization, as it may lead to overfitting, for example, if the model becomes too focused on the training data. Now let's discuss the importance of choosing the right loss function when working with empirical risk. Selecting an appropriate loss function is critical because it allows us to tailor our approach to the specific problem we are trying to solve. And whether we are dealing with a classification regression, the choice of loss function has a significant impact on the model's performance and how well it learns from the data. And by carefully choosing the loss function, we can ensure that our model is optimized for the unique demands of the task. It's similar to providing the right tools for a specific job. Each loss function brings a different perspective to model optimization and ensuring effective performance and meaningful outcomes. And next, we will explore some special cases of risk formulation that help illustrate different scenario where loss function choice is essential. For example, binary and multi-category classification, and in general for classification tasks where the output label can be belong to one of several categories, we often use the 0-1 loss. This loss function assigns a value of 1 when the predicted output does not match the true label, and 0 otherwise. And the risk in this case is represented by the probability that the predicted value does not equal the true label. And this probability essentially quantifies the likelihood of making an error of new data, and it's fundamental measure of model performance. And in context of regression problems, we use a different approach. Here, the loss function is typically the square difference between the predicted and actual values, often called square loss. And the risk is then defined as the expected value of these square differences, providing a measure of how far of our model's predictions are on average. And this helps in understanding the average predictions error across the entire input distribution. And this formulation highlights how different types of problems require specific risk definitions, with the goal always being to understand and minimize the prediction error for both training and new data. Now let's focus on the empirical formulations for the specific cases we discussed earlier. In the context of classification, empirical risk is computed as the average of the 0-1 loss across all training samples. This means that for each training sample, we check whether the predicted label match the true label. If they don't match, the loss is 1, otherwise it's 0. And by averaging these values over all training data points, we get the empirical risk, which tells us how frequently our model makes errors on the training set. And for regression tasks, empirical risk is computed by averaging the square differences between the true and predicted values for all training examples. This is known as the mean squared error. It quantifies how far of our model predictions are from the actual values on average. Okay, in both cases, n represent the number of training samples, and f of xi is predicted value of the input xi, and yi is the true value. And the empirical risk gives us a practical way to evaluate model performance using available data, with the goal of minimizing this value during training to achieve better accuracy. To move forward from our previous discussion on expected risk, let us now explore how we determine the optimal prediction function that can minimize this risk, regardless of training data available. This brings us to the concept of Bayes risk and the Bayes predictor. Bayes risk represents the lowest possible risk that can be achieved for a given problem, assuming complete knowledge of the true data distribution. And we start by defining the expected risk. which can be described as the expected value of the loss function between the true output y and the predicted value f of x. More specifically, we have r of x equals the expected value of L or y and f of x. In other words, we are calculating the average value of the loss over all possible outcomes of y and the predicted value of f of x. And the further analysis of this, we can use the concept of conditional expectation along with the law of total expectation. This means that the expected risk can be written by conditioning on the input x. In this form, we write r of f equals the expected value, where we take the expected value of L of y and f of x given x. Essentially, this means that first we calculate the average loss from each given input x, and then we calculate the overall average across all possible values of x. We can also represent the expected risk using an integral. We say that r of f equals the integral over x of the expected value of L of y and f of x, given that x is equal to x dash times p of x dash. This integral representation shows how we average the loss over the entire input space, considering how likely each input is by weighting it by its probability. And the bias predictor is the function that minimizes this expected risk. It's the theoretically optimal predictor, as it takes into consideration all possible inputs and their corresponding distributions to make the most accurate predictions. And the integral representation of the expected risk illustrates how the loss is averaged over the input space, weighted by a likelihood for each input. In conclusion, the Bayes predictors serve as a benchmark representing the best possible model we could create if we had full knowledge of the data distribution. And the ideal solution for our goal in practical machine learning is to approximate this ideal as closely as possible, even though we rarely have perfect information about the underlying data. Now let's explore the concept of conditional risk and how it's used to minimize overall risk. For any given input value, we can define the conditional risk as the expected loss for a particular prediction, conditioned on knowing that specific input. This means calculating how much error we expect if we make a prediction, given that we know the current input value. And specifically, we denote conditional risk as r of z given x dash equals expected value of L of y and z given x equals x dash. The overall expected risk can then be derived by averaging this conditional risk over all possible values of the input, weighted by how likely each input is. We express this as r of f equals expected value over x dash of r of f of x dash given x dash, or r of f equals the integral over x of r of f of x prime dash x dash given x dash times p of the x dash. To minimize the expected risk, we seek to determine the best predictions for every possible input value. And this process can be described as finding some value by treating each input independently. We can determine the optimal outcome for each case, thus minimizing the total error across all inputs. Let's turn our attention to the concept of minimized risk and the role of the Bayes predictor in achieving this. The expected risk we covered earlier can be minimized by the Bayes predictor. And essentially, the Bayes predictor is the function that provides the most accurate prediction, leading to the lowest possible risk. For each input value, the Bayes predictor selects an output that minimizes the conditional risk, meaning it minimizes the expected loss given that particular input. And the Bayes risk represents the smallest average error that can be achieved using the Bayes predictor. It's calculated as the expected value of the lowest possible loss for each input, taking into account the probability of each input occurring. This risk gives us an understanding of the theoretical best case scenario where the predictor error is minimized to the greatest extent possible. And it's worth noting that a couple of points about the Bayes predictor. First of all, it's not always unique. There can be multiple functions that achieve the same minimized risk. And however, all such predictors will have the same Bayes risk. For instance, in binary classification, when the probability of each class given an input is equal, multiple predictors may yield identical performance. And the Bayes risk is typically greater than zero, except in cases where there is perfect deterministic relationship between the output and input. And in most real-world scenario, there will be some degree of uncertainty or noise leading to a non-zero risk, even for the best possible predictor. And now, turning our focus to excess risk, let's understand it's important in evaluating model performance. The excess risk of a function represents the difference between the actual risk of a given model and the Bayes risk, which is the minimum possible risk achievable by the best possible model. In other words, excess risk tells us how much worse a model performs compared to the theoretical best case scenario. And the excess risk is always non-negative, as it measures the gap between the performance of our model and the optimal performance that can be achieved. It quantifies how much extra error our model incurs beyond what could be minimized by an ideal predictor. And here are some key points to understand about excess risk. Again, it's measure how much worse the given model is compared to the optimal Bayes risk, which would achieve the smallest possible error. It serves as a way to compare the performance of a real model with the theoretical best. And a smaller excess risk means that the model's performance is closer to the ideal, suggestion that is generalized as well and captures a relationship in the data effectively. And again, minimizing the excess risk, it's an important goal because it means bringing our model's performance closer to the optimal. And achieving a low excess risk indicates that our model is not only fitting the training data well, but also performing nearly as well as the best model we could theoretically aim for. Focusing now on binary classification, let's take a closer look at the Bayes predictor for this specific case. And for binary classification, we consider a situation where the possible outputs are either 0 or 1. And the Bayes predictor is designed to minimize probability of making an incorrect prediction. In other words, it chooses the output that has the highest conditional probability given the input. And to achieve this, the Bayes predictor selects the value that maximizes the probability of correctly predicting the class label based on the given input. Specifically, it will choose 1 if the probability of the output being 1 is greater than 1.5. And it will choose 0 if the probability is less than 1.5. And again, the Bayes risk is defined as the expected value of the minimum error for each possible input. And the Bayes predictor essentially acts as an ideal classifier that select the most likely outcome for each input based on the underlying distribution. Moving on to multi-category classification, we extend the concept of the Bayes predictor to scenario with more than 2 possible classes. In this case, the output can belong to one of several classes labeled from 1 to k, where k is greater than or equal to 2. And the Bayes predictor for multi-category classification chooses a class label that has the highest probability given the input. Essentially, for each input value, it selects the class that is most likely based on the available information. And this is a natural extension of what we previously discussed for binary classification. Instead of choosing between 2 classes, we're now dealing with multiple possible outcomes. But the goal remained the same, to minimize classification error by selecting the most probable class. Okay, and here we can see key point to consider. The Bayes predictor selects the class with the highest conditional probability for any given input. This approach allows each input to be assigned to the class that is statistically most probable. And it's important to mention that there's Bayes predictors and risk apply specifically to the 0-1 loss, where every type of misclassification is penalized equally. And practical applications such as, for example, let it be spam detection, errors may not have the same consequences. And thus, a different version of Bayes predictor would be required to account for the asymmetric costs of different types of errors. For regressions, Bayes predictor takes a slightly different form compared to classification settings. In regression, the possible outputs are real numbers, and the loss function is typically the squared difference between the predicted value and the actual value. And the Bayes predictor is in this context, is the value that minimizes the expected square loss for a given input. And to find this Bayes predictor, we consider the conditional expectation. For a given input, the optimal predictor is simply the expected value of the output, conditioned on that input. This makes sense because choosing the conditional expectation minimizes the mean square error, This is our object in regression settings. Thus, the bias predictor in regression is the, again, conditional expectation of the input given the input. It provides a more accurate estimate by averaging all potential outcomes weighted by their likelihood. Now let's dive into the code example and see what it does step by step. I wanted to show example how we can use some loss function in a different scenario. And first, we start by generating some data for our regression example. We begin by setting a random seed with NP random. This is step important for comparing, meaning that every time we run the code, we will get the same random numbers. It makes the experiments consistent and easiest to debug. Next, we generate our input data, X. We create 300 random values between 0 and 2, and you can think of X as our feature or input variable that we will use to make predictions. After that, we generate Y, which is our target variable, and we use a simple quadratic equation. Y equals 4 plus 3 times x squared, and add some random noise to it. And why it's important? Because this random noise is meant to simulate the variability typically found in real world data, and making our data set more realistic. Then we split the data into training and testing sets. We take the first 80 samples from X and Y to create our training set, X train and Y train. This is the data our model will learn from. And the remaining data is used for the testing set, X tests and Y tests. These values are used to evaluate the model after it has been trained. And then we, of course, want to test on unseen data, which helps us to understand how well the model generalizes to new information. Now moving on, let's move into the process of training different regression models and evaluating their performance with various loss function. So first, we assign colors and markers for visualization purpose. This will help us easily differentiate between the different loss functions when we plot the results. Next, we loop through each of these loss functions we want to explore. For each loss function, we create a separate model. Now I use stochastic gradient descent regressor, and this approach allows us to train a linear regression model using just the different loss functions. And essentially, stochastic gradient descent is a way of optimizing the model by iteratively adjusting its parameters in the direction that reduce the loss based on the calculated gradient. And of course, this process helps us compare how each loss function affects the performance of linear regression when trained using gradient-based learning. And after training each model on the training data, we then make predictions on the test data. These predicted values allow us to see how well the model has learned from the training phase. And once we have the predictions, we calculate specific loss values in order to evaluate how well each model is performing. And depending on the type of loss function we used, we calculate a suitable error metric. For instance, if we use the squared error loss function, we compute the mean squared error to understand the magnitude of errors in the model's predictions. And to make the mathematical aspects clear, we also display the formula for each loss function This helps to bridge the gap between the code and the theory behind it, ensuring we understand the different way in which each model measures error. We then proceed to visualize the performance by plotting the predicted values against the actual values for each model. And in this plot, we use distinct color and markers for each loss function, allowing us to compare the performances easily. On each plot, we also draw a prediction line representing where all points would lie if the model made perfect predictions. And this allows us to visually assess how far off the predictions are from the ideal scenario. Now let's take a look at the visualization of our regression model performance using mean square error. In the scatter plot, we see the actual values on the x-axis and the predicted value on the y-axis. And here the blue dots represent each individual prediction made by the model. And the red dashed line shows the ideal prediction line, where the predicted value would perfectly match the actual values. And the closer the blue dots are to this red line, the better model's predictions are. If all the dots were perfectly aligned along the red line, it would mean that our model is making perfect predictions. However, as we can see, there are deviation, meaning the model doesn't always predict perfectly, which is expected with the real-world data. And here we can see the MSE error, which is reported here is approximately 1.7, quantifies this deviation by averaging the square difference between the actual and predicted values. A lower MSE value would indicate that the model is performing well, as it suggested that predictions are closer to the true value. Moving forward, let's examine the performance of our model using Haber laws. And is an interesting combination of mean square error and the mean absolute error. And it's designed to be less sensitive to outliers by having like squared error for small differences and like absolute error for larger difference between the predicted and the actual value. And this combination naturally makes it a good choice when we want to balance robustness to outliers, so with the smooth gradients for optimization. Here we notice that the predictions are more scattered compared to the MSE plot we saw earlier. So the mean square error value of 40.6, which is quite high, tell us that the predicted value deviates significantly from the actual values. And this is a clear indication that for this data, using Haber laws didn't yield the most accurate predictions. And the loss value of Haber laws is 3, which provides a measure of how far the predictions are from the actual value based on the specific formulation of the Haber laws function. And again, overall, while Haber laws is effective in scenario with many outliers, it seems that in this instance, it may not have provided as good a fit as other loss functions, likely due to characteristic of the data we are using. Next, let's look at how our model performs with epsilon insensitive loss. And this loss function is designed to ignore small differences between the actual and predicted values. Basically, it allows a certain margin of epsilon where errors are not penalized. This helps the model to focus on more important differences and ignore very small errors that might just be noise. Here we notice that the most of the predictions are quite close to the line, which is a good sign. And the MSE for this model is 2.1, meaning that the overall error is moderate and generally better compared to early examples, like with yes, hybrid loss. And the lowest value of this approach is 0.03, which indicates a small average deviation between predicted and actual values. This means the model is doing a good job of ignoring small differences and focusing on making accurate predictions for the bigger picture. And our next example, square epsilon insensitive loss. This type of loss is quite similar to the epsilon insensitive loss, which is discussed, but with a slight twist. Instead of ignoring small differences, it squares those differences that fall outside the given margin. And this means that once error exceeds a certain point, they start to matter more, emphasizing large deviations. In this graph, we can see that many of the predictions are quite close to the line, meaning that the model did a pretty good job overall. And the MSE for this model is 1.6, which is an improvement compared to some previous approach. And this indicates that the model's predictions are generally close to the actual values. The lost value is reported as 0.88, which is relatively low and indicates that on average, the model's predictions aren't too far off from the actual values. So the squared epsilon insensitive loss helps the model give more weight to significant errors while ignoring minor ones, which can be helpful in balancing accuracy and stability. And overall, this loss function seems to perform well, resulting in I guess, a good balance between ignoring small noise and emphasizing large mistakes. So I guess we can skip this part and we just proceed with the classification example and see how different loss function affect our model's performance. And then we here use stochastic gradient descent classifier to train the model for each of the chosen loss functions. And here we are considering log loss and hinge loss to see how they affect the model's ability to separate the classes effectively. And yes, if in regression we used gradient descent to minimize the error between predicted and actual values. For classification, the concept is very similar. Here, the goal is to make the model correctly assign data points to different classes. And the stochastic gradient descent classifier works by adjusting the parameters of a decision function, such as a line or boundary that separates the different classes. It uses a loss function like log loss or hinge loss to determine how incorrect the model is at each step. And then it adjusts the parameters to reduce that error. Let's examine the performance of our model using the log loss function, also known as the cross entropy loss, is used to evaluate how well a classification model predicts the probability of the correct class. It penalizes false predictions, and the penalty increases as the predicted probability diverges from the actual label. And the goal is to minimize the log loss when it leads to high accuracy and better model predictions. And in the graph here, we have the decision boundary. I draw between two classes, one represented in yellow and the other in purple. And their data points uploaded in their respective colors. And we can see where they fall in relation to the decision boundary. Ideally, each point should fall into the correctly colored region. As a log loss value reported as 0.2, it's a measure of the average penalty of misclassified predictions. A lower log loss indicates that the model is confident in its predictions and is mostly correct. In addition, we see an accuracy score of 0.9, which means that 90% of the predictions made by our model were correct. We can observe that the decision boundary is well positioned, meaning that it effectively separates the majority of the yellow and purple points into their respective regions. However, there are still some data points close to the boundary that might be incorrectly classified or less confidently predicted. Now let's focus on how the hinge loss function shapes the decision boundary of the model. Yes, we can compare with the previous one. And the hinge loss is used in the classification to maximize the margin between classes. This means it encourages the decision boundary to be as far away as possible from the nearest points of each class. And it penalizes not only misclassified points, but also those that fall too close to the correct classification boundary. And the loss value here is 0.2, which represents the current average penalty for the model's predictions. And the lower value indicates that the model is confident in its predictions. The accuracy of 0.92 means that the model correctly predicted the class of 92% of the data points. And the decision boundary is quite distinct, effectively divided into two classes. Hinge loss helps create a clearer separation, allowing the model to distinguish between classes with minimal error. Again, we can compare. Here we explore the modified hybrid loss function and its impact on model performance. And the modified hybrid loss function combines elements of hinge loss and squared error, aiming to leverage the strengths of both. It applies penalties to misclassified points and those near the decision boundary, but adds a square term for points that are confidently wrong. And this combination approach is designed to balance maximizing the margin with providing smoother penalties. With a loss value of 1.1 and accuracy of 0.85, the model using modified hybrid loss correctly classifies about 85% of the examples. This makes it particularly effective at maintaining accuracy while remaining less sensitive to outliers. Okay, and the next example, we observe the result of using the squared hinge loss function. And the squared hinge loss builds on the traditional hinge loss by squaring the margin-based penalty. And the decision boundary here remains quite similar to what we saw with the original hinge loss. However, the squared nature of the penalty function means that the larger errors were points on the wrong side of the margin, and of course, are heavily penalized. This is evident from the high loss value of over 3 billion, and this large value indicates that even through the accuracy, it's still relatively high at 91%. The squared hinge loss exaggerates any discrepancy. which leads to significantly larger penalty contribution from misclassified samples. And of course, when comparing different loss function across both regression and classification tasks, it's clear how critical the choice of loss function is in define the model's behavior and its success. The loss function fundamentally shapes how model learns by dictating how errors are penalized, which in turn influences both the accuracy and robustness of predictions. And again, the loss function defines what good performance looks like to the model, and thus directly impacts both training and generalization capabilities. I guess that's all for this lecture. Thank you so much. Maybe some questions or comments. Okay, thank you. We'll see you on the next lecture.
Yes, thank you. Okay, and there's still another lecture just after 50 minutes.
Yes, we will have lecture in 15 minutes. Yes.
About the point process. Yeah.
Okay.